In this video, we're going to be discussing Algebra 2, Chapter 1, Section 1, Expressions. An expression is an algebraic expression in the context of Algebra 2, and it is an expression that is built from one or more constants, variables, or algebraic operations. A constant might be the numbers we're used to, such as 2, 5. Or maybe a constant has a letter, such as E, which represents a specific number, or C. For instance, in physics, C might mean the speed of light, or pi, which is a geometric constant that appears a lot in geometry and other fields. Or an algebraic expression may also contain a variable. Variables will always be represented with an abstract symbol, such as x or y, and we're familiar with these abstract symbols from Algebra 1. An algebraic expression also can have any number of algebraic operations, such as addition, subtraction, division, except by 0, exponentiation, so 2 cubed, and grouping operations, such as parentheses, 3 plus 7 times 4. Now, a few notes. In Algebra 2, whenever we use parentheses, we will not write the multiplication symbol in between the parentheses and the thing being multiplied. That will be assumed. If it's a plus, we'll write plus here, or minus, or divide. Also, there are some operations that are inherently grouping, like the long fraction bar, 3 over 7 plus 2. In this case, 7 plus 2 happens first because it's under the long bar. What do we not have in an expression? An expression must not contain equals. So no equals. Expressions can be evaluated. What does it mean for an expression to be evaluated? What it means is that we give a value to any symbols and we find the overall value of the expression. For instance, we might have the expression 3x plus b all times 2. And we're given x equals 4, b equals 5. Now these are not expressions. They're actually defining the value of these constants or variables for the purpose of evaluation. So now let's evaluate. We plug in 4 when we see x, and I'm going to use parentheses when I plug in to prevent me from accidentally changing the order of operations, which we'll talk about in a minute. So plugging in 5 for b and 4 for x, we can evaluate the expression. 3 times 4 is 12. 12 plus 5 is 17. And 17 times 2 is 34. So we now know the value of this expression with the given values of the variables and constants to be 34. We can also describe an expression verbally. For instance, we might describe an expression in the way that's written on the slide to the left. First, square the radius and multiply the result by 2 pi. Then take the product of the radius and the height and multiply the result by 2 pi. Finally, add the result of the calculation. So we can build up an expression from the verbal description. Squaring the radius, so we'll use r to mean radius. R squared. Multiply the result by 2 pi. 2 pi. Then take the product of the radius. So this is a new sub-expression of our total expression. So radius and the height, we'll use h for height, and multiply that result by 2 pi. Finally, add the results of the two calculations. Now we can do some reordering. We can multiply in either order and get an expression like this. 2 pi r squared plus 2 pi rh. This is example 4 in the book. Let's work example 5, part B. Example 5 says, in each of the following pairs, the second expression differs from the first by the introduction of parentheses, which is a grouping operation. Explain what difference this makes in the calculation and choose values of the variables to illustrate the difference. So for part B, we have 2, and I'm going to write my L a little different than the book, L plus W. Why did I write my L that way? I don't want it to be confused with the number 1. And the other version of this expression is 2 parenthesis L plus W. So the difference is that in the first one, we multiply 2 and L first. And the second one, we add L and W first. Now this will result in this will give us a different result when we evaluate for different values of L and W. Well, let's choose some values of L and W to make this obvious. Let's use L of 0. Why 0? 0 is an easy one to use if there's no division. And W, let's try 3. Let's plug in our values. 2 times 0 plus 3 for the first version here. 2 times 0 is 0. 0 plus 3 is 3. The second version will have 2 times 0 plus 3. Now we're going to add 0 and 3 first, which is 3, and then multiply to get 6. We can see those are different values. So by adding parentheses, we changed the nature of the expression. That brings up the order of operations. The order of operations during evaluation is critical. First, we have to follow any parenthesis or grouping operations. As we saw in the previous example, these parentheses are critical. Then we need to do any exponentiation. We didn't have any in this example, but any powers, such as the r squared here, this needs to happen before the multiplications. Then multiplication, division, and then addition and subtraction. It's a little hard to remember this order, so there's a mnemonic we can use. Please excuse my dear Aunt Sally. For parenthesis, exponentiation, multiplication, division, addition, subtraction. Please excuse my dear Aunt Sally. So the first letter of each word in the mnemonic is the first letter of the corresponding operation. Or, as a former student of mine decided, why not just remember the whole word, PEMDAS? So if you just think PEMDAS, that's the order of operations. Parentheses, exponentiation, multiplication, division, addition, subtraction. Now, the multiplication and division and the addition and subtraction can actually be reordered and regrouped because multiplication and division can be done in either order. For instance, 2 times 3 divided by 2 is the same as 2 times 3 divided by 2. And that's the same as 3 divided by 2 times 2. Now it's important to not get mixed up and get your numerators and denominators backwards with the division, but you can reorder division and multiplication. Same with addition and subtraction. We're familiar with this. 7 plus 3 minus 2 is the same as 7 plus 3 minus 2. That's the same as 3 minus 2 plus 7, which we can also write this way. And those are all the same value. So the order that we evaluate in is not always critical. 7 plus 3 is 10. For multiplication, and for addition and subtraction, it's not critical. And for multiplication and division, it's not critical. But you can get the same answer by adding and subtracting in either order, and multiplying and dividing in either order. But we must first do any parentheses and then do any exponents before we do the multiplying and dividing. We must do any multiplying and dividing before doing any adding or subtracting, or we'll get the wrong result when we evaluate expressions. So let's do an example. A corporate bond. So in this example, we are going to be constructing an algebraic expression from a written English description. So these word problems, I like to say this to all my students, word problems are the hardest kinds of problems that we do in math, do in Algebra 2, because they involve taking a scenario in the real world, or as close to the real world as we can get to create an example or a problem. And we have to take that and turn it into essentially the math language or the algebra that we use to describe these problems. We have to apply the rules that we've learned and that we will learn in the class to the algebra, to the numbers, to the equations, to the expressions, to get a result. And then we have to take the result and go back and reinterpret that in terms of the original real-world problem. This is a lot of thinking and also a lot of translating between something that's written and something that's abstract and back to something that's written. I think this involves both parts of your brain, and you have to be able to think with both parts of your brain. So this is a very good exercise to help us grow in our ability to use the brains that we've been given to the best of their ability. So we'll be doing a lot of word problems in our assignments in Algebra 2. So here's the first. Expressions. Example 9. A corporate bond has a face value of $P. Whenever I'm doing a word problem, I like to have a sheet of scrap paper, and I'll just start writing down things in algebra or symbols. So the bond has a value of $P. So I'm just going to write this down to help me understand the problem. There is interest each year of 5% of the face value. After T years, the total interest is the product of the number of years T and the interest received each year. Write down T years. The payout is the sum of the face value and the total interest. Let's just write a simple little equation. Payout, whenever you see the word is, think equals. Payout equals the sum of the face value and plus, since it's a sum, total interest. Okay, so if you don't write things down and you read a long word problem like this, your eyes will glass over and you will just feel like it's hopeless. So I like to write things down to help me start to break the problem apart into little pieces to help me understand it, and to help me to start write some of the math language, the algebra, that we're going to need to use to solve the problem abstractly. So in this case, we're only trying to create the expression, but later on in the class, we're going to actually solve an equation and get a result. So first, the part A says, write an expression for the total interest after t years. Okay, so the face value is maybe this is important to think about. The face value is printed on the bond. Think of a piece of money. It could be a $5 bill. Now, a piece of money is not a bond, but there will be a number written or printed on the bond. That's the face value. Now, we don't know the face value, so we have to use a constant, and I'm going to call it a capital F. F is face value. Okay, that helped me write my expression more quickly. So, write an expression for the total interest after t years. So, each year we get 5%. What is percent? It's a quick little thing to talk about. Per cent is a Latin word which means 400, or each 100. In other words, 5% is 5 hundredths, or 5 over 100. Okay, so 5% is a quick way of saying 0.05. And we will always use this symbol to mean percent, which is a quick way of thinking of a number over 100. So our total interest will be 5% times the face value, capital F, remember we gave it this definition, times the number of years. Now, we don't have to write the dot to mean multiply, or even an x. We don't ever use an x in this class for multiply. We never write this. This is no good in Algebra 2. Why is that? Because it looks too much like the variable x. So we'll use a dot to mean multiply if we really need to be explicit, which is almost never. Usually, multiplying will just be implied when we write a number next to a letter. That's 3 times x. Or if we write an expression with the parenthesis, this means multiply. So this means 0.05 times f times t. And that's the answer. This is an expression for the total interest. Whenever we have the final answer for a problem, we need to square it or circle it. This way, whoever is grading the problem can quickly see the final answer. B. Write an expression for the payout after t years. So we already, when we were thinking of the problem, wrote this down. And we can reuse this. The payout will be the face value, F, plus the total interest, which we got in problem A, 0.05 F times T.